Hi there, I want to get you some more examples of solving polynomial equations. So remember the general setup. We have a polynomial equal to a polynomial. We always get 0 on one side, so it'll give you some polynomial equal to 0. And then just remember there's these two basic cases. If the constant equals 0, you can factor that to solve it. All right, but the question is, what about when the constant's not equal 0? And that's where we got to go through all this theory stuff. So, just to remind you of the steps, when you're trying to solve p of x equals 0 when the constant's not equal 0. So the first thing you do is use the rational roots theorem to list all the possible rational roots. All right, and that's going to be a plus or minus factor of the constant over a factor of the leading. One thing about this, usually signs are important in math, right? But in this particular case, because of that plus or minus in front, if your constant or your leading is negative, you can ignore that negative. We'll see an example of that in just a second. All right, so anyway, you get a list of all the possible rational roots. Then you use your calculator to try to find which one of these actually solve the equation. Remember that we're solving p of x equals 0, and so for one of these to solve the equation, I should be able to plug this into my polynomial and end up getting 0 at the end. I'm not sure if I explained that very well in class. All right, well, how do you figure out which ones do? I would take advantage of your calculator, and you can either go to your table feature and guess and check through that list until you finally find one that works, or you can graph it. And remember, setting p of x equal to 0 is the same as finding the x-intercepts. So you graph it and try to look at the x-intercepts and look if any one of these is actually an x-intercept. If you do it that way, it's more of a visual way. If you do that, though, I would highly advise going back to the table and plugging that number in to make sure that it actually works. All right, so like I said a minute ago, whatever your guess is, for it to be a solution, you should be able to plug it into your polynomial and it should give you 0. All right, so let's look at some examples. Oops, I got ahead of myself, sorry. Once you do have a solution, what you want to do is you want to run that through the synthetic division, and you should get 0 at the end. That number is called the remainder. If you remember, division's really going on behind the scenes. And so you should get 0. And the key thing is, if you verified beforehand with your calculator that it will give you 0, then you go through the synthetic division and don't get 0. That tells you that you made a mistake somewhere with your synthetic division, which is easy to do. Okay. Now, furthermore, you should get 0, but the numbers to the left of that 0 are important. Those numbers are they give you what's called the quotient. Those are the coefficients of the quotient. It's always 1 degree less than what you started with. So if you started with a third degree equation, this will give you a quadratic. All right. If you started with a fourth degree equation, though, this will give you a third degree. All right, so what you're trying to do at that point is solve the quotient equal to 0. In most problems, you're going to start with the third degree. This will be quadratic, and so now you can use the quadratic formula to finish solving that problem. And then here's the important thing. If that quotient isn't quadratic, you basically got to go back to your list, find another one that works, and repeat the process, but only on the quotient. Okay, we'll see an example of that in a minute, if that seems a little vague. So let's look at an example. Let's look at this polynomial equation right here. So we have this polynomial equal to 4. In the theory, you can actually think about constants being a polynomial. So this is really a polynomial equal to a polynomial. But we always get 0 on one side, so we end up with this polynomial equal to 0. So this is that on the left side is that p of x I keep referring to in this problem. So you go and crank it through your rational roots theorem, plus or minus a factor of the constant. This is what I was talking about a minute ago. Notice that constant's really negative. This is one of the rare cases where you can actually ignore that negative. So we can just look at factors of 3 over factors of 2. You can ignore that negative as long as you remember to put the plus or minus out front. All right, so the factors of 3 are 1 and 3, and the factors of 2 are 1 and 2. So you just come up with some algorithmic way to list all those possibilities out. The way I always do them is I do each one of these numbers over the first denominator, each one of these numbers over the second denominator, and so forth if the list is longer. Okay, so there's our list. It's actually pretty basic in this problem. 1 over 1, 3 over 1, 1 over 2, and 3 over 2. Again, don't forget that plus or minus. I've just seen too many students get totally frustrated by this, and then it's usually because they're forgetting to look at the negatives as well. All right, reduce things down too. So those first two numbers are 1 and 3. Okay, now you might want to practice this now, and so try to find one that works. So you might want to pause it, but the idea is now you go to your y equals, plug your equation in, and you can do it one of two ways. You can graph it now. Here's the graph, and look at it carefully. We're only looking to see if any of these 8 numbers are an x-intercept. If you look carefully, it kind of looks like -2 is, but -2 is not in our list. All right. If you look really carefully, you might not show up on the video, but that is actually falling a little bit short of +1. But if you look right there, that's right at -1. All right. Like I said, though, don't just assume that's right because you can have some graphing effects. So if you're going to use the graph to find them, then go to the table and actually plug in -1 to verify that you do get that 0 there. I don't know how well it's showing up on the screen, but that actually is giving me, oh, it's not going to focus. That actually is giving me 0. The other way to do them, it just might be longer for some problems, is just start going through the list. This one, you get to it pretty quick. Just start going through the list. The first possibility is +1. That gives me 4, so that doesn't work. And then my next possibility is -1. That gives me 0. Okay? All right. So we finally figured out that x equals -1s. Especially if you do this graphically, though, make sure to go to your table and verify. That way it'll catch any errors on the synthetic division step. All right, so you plug that. Remember how to do synthetic division. You plug your solution into the box. Now I want to show you something. Okay, so here's the coefficients of p of x, right? And so I go through my synthetic division like that, but look what happens. That's not equal to 0. All right, but I verified. I know this should work. All right, so that tells me I did something wrong right here. Okay, so don't force that 0. You know, you're going to be doing homework and you're going to say, oh, I must have made a sign error. I'm going to write 0 here. All right, that's telling you something. Something's wrong. And so I intentionally did that to remind you of something too. But also that's a good lesson there is don't force your 0 at the end. Use that as a check to make sure you did all this correct. All right. So what I don't know if you've noticed what went wrong here, but notice this was 2x cubed, this is 5x squared, and then this is -3. I was missing a power of x. All right, so remember, if you're missing a power, you need to fill in a 0 for it. So now you go through your synthetic division, you will get 0 at the end. What's important is these 3 numbers now. Okay, I started with the 3rd degree, so these are the coefficients of my quotient, and I started with the 3rd degree equation, so now this is 2nd degree, i.e. it's quadratic. All right, and so it's 2x cubed plus 3x minus 3 equal to 0, and so I can go through my quadratic formula now, and you end up getting down to here. This doesn't simplify at all. So we're getting our solutions now. Try to remember to include. Remember, we found that initial solution at the beginning. It's easy to forget to list that as an answer after you've been through all that work. Okay, let's look at a 4th degree equation. So this big hairy looking thing, but one nice thing is we're already equal to 0, so we don't have to do any pre-work there. So there's our p of x. So we go to the rational roots theorem. This one's pretty complicated. Factor of 15, that's my constant, over a factor of 6, that's my leading. Factors of 15 are 1, 3, 5, and 15. Factors of 6 are 1, 2, 3, and 6. So I got to list all of these things out, and so you really want to come up with a systematic method to go through that. And like I said, I do all the numerators over the first denominator, all the numerators over the second denominator. So there's all the numerators over the first denominator, over the second denominator, over the third denominator, over the fourth denominator. Okay, especially if you're going to use the guess and check method, but maybe in general, a lot of times, especially with these big lists, things will start repeating. So you can look through, like right here's 3 over 3, that's equal to 1, so that one's already taken care of. 15 over 3 is 5, that's in my list already, so I can take that one out. 3 over 6 is a half, it's also in my list. 15 over 6 is 5 5/2, that's also in my list, so I can take it out. All right, breaks it down a little bit. You might want to pause here real quick. So now what you want to do is figure out which one of these work into this equation. So you'd use your graph or your table. You might want to pause just to see if you can find it on your own there. But after you've done that, hopefully you end up seeing now there's actually two that work, so you may have found another one. But x equals -1/2 works. That's the first one I found. All right. So I ran it through the synthetic division. I got my 0, so good news. The thing is, look at this quotient. That should cue you in. It's longer anyway. But you got to think about what's the degree of that quotient. I started with a 4th degree, so this is 3rd degree. All right. You could write it out if you wanted to. It's 6x cubed minus 10x squared minus 18x plus 30 equal to 0. The key thing is you don't need to restart the process with this. Okay. You don't need to. You can come up with a new list. It'll be slightly shorter, but you don't have to. The key thing is you want to repeat the process. But whenever you do the synthetic division, you want to work with this, not the original. Okay. I'm going to point that out in just a second. So what you want to do, you don't have to plug this function in, like I said. What you want to do is you just want to go back to your list and find a second one that also works in your equation. Okay. So again, you might want to pause it and see if you can find one. All right. And but once you get there, hopefully you end up seeing that 5/3 also works. Okay, so we want to run it through the synthetic division, but like I said, you want to run it through on the quotient, not the original. The idea is we're trying to get down to a quadratic that we can eventually solve. So 5/3, remember this was my quotient, so I'm going to run 5/3 through it. You can pause it to make sure you can get all those numbers, but that's what you end up with. We have our 0. Now, this was 3rd degree, so now this quotient is 2nd degree. And so that's quadratic. So it's 6x squared plus 0x minus 18. I'm going to set that equal to 0. And because of a student's comment the other day, I'd prefer you to go through this with the quadratic formula just so you don't forget that plus or minus there. Alright, so you end up getting this. This one's kind of interesting. That's a pretty big number, but notice you can still use a factor tree on it. Just takes a little bit longer, but you just start dividing by 2 over and over until you end up getting to a 22 times 27. That's 3 times 9 and 3 times 3. And then just remember, each pair comes out. So I got a 2 times a 2 times a 3, but there was one 3 left under the radical there. Alright, so that's 12. So we get 12 square root of 3 right there. Alright, so as far as that x goes, we have x is plus or minus 12 square root of 3 over 12. The 12's cancel. I get plus or minus square root of 3. So we got the problem solved. We just got to remember what all our solutions were. They were -1/2, 5/3, and then those 2 square roots. Alright, I hope those examples help.